General relativity is a theory of gravitation that was developed by Albert Einstein between 1907 and 1915. According to general relativity, the observed gravitational effect between masses results from their warping of spacetime. By the beginning of the 20th century, Newton's law of universal gravitation had been accepted for more than 200 years as a valid description of the gravitational force between masses. In Newton's model, gravity is the result of an attractive force between massive objects. Although even Newton was troubled by the unknown nature of that force, the basic framework was extremely successful at describing motion. Experiments and observations show that Einstein's description of gravitation accounts for several effects that are unexplained by Newton's law, such as minute anomalies in the orbits of Mercury and other planets. General relativity also predicts novel effects of gravity, such as gravitational waves, gravitational lensing and an effective gravity on time known as gravitational time dilation. Many of these predictions have been confirmed by experiment, while others are the subject of ongoing research. For example, although there is indirect evidence for gravitational waves, direct evidence of their existence is still being sought by several teams of scientists in experiments such as the LIGO and GEO 600 projects. General relativity has developed into an essential tool in modern astrophysics. It provides the foundation for the current understanding of black holes, regions of space where the gravitational effect is so strong that even light cannot escape. Their strong gravity is thought to be responsible for the intense radiation emitted by certain types of astronomical objects. General relativity is also part of the framework of the standard Big Bang model of cosmology. Although general relativity is not the only relativistic theory of gravity, it is the simplest such theory that is consistent with the experimental data. Nevertheless, a number of open questions remain, the most fundamental of which is how general relativity can be reconciled with the laws of quantum physics to produce a complete and self-consistent theory of quantum gravity. From special to general relativity. In September 1905, Albert Einstein published his theory of special relativity, which reconciles Newton's laws of motion with electrodynamics. Special relativity introduced a new framework for all of physics by proposing new concepts of space and time. Some then accepted physical theories were inconsistent with that framework. A key example was Newton's theory of gravity, which describes the mutual attraction experienced by bodies due to their mass. Several physicists, including Einstein, searched for a theory that would reconcile Newton's law of gravity and special relativity. Only Einstein's theory proved to be consistent with experiments and observations. To understand the theory's basic ideas, it is instructive to follow Einstein's thinking between 1907 and 1915. From his simple thought experiment involving an observer in free fall to his fully geometric theory of gravity. Equivalence principle: a person in a free-falling elevator experiences weightlessness and objects either float motionless or drift at constant speed. Since everything in the elevator is falling together, no gravitational effect can be observed. In this way, the experiences of an observer in free fall are indistinguishable from those of an observer in deep space, far from any significant source of gravity. Such observers are the privileged observers Einstein described in his theory of special relativity. Observers for whom light travels along straight lines at constant speed. Einstein hypothesized that the similar experiences of weightless observers and inertial observers in special relativity represented a fundamental property of gravity, and he made this the cornerstone of his theory of general relativity, formalized in his equivalence principle. Roughly speaking, the principle states that a person in a free-falling elevator cannot tell that they're in free fall. Every experiment in such a free-falling environment has the same results as it would for an observer at rest or moving uniformly in deep space, far from all sources of gravity. gravity and acceleration. Most effects of gravity vanish in free fall, but effects that seem the same as those of gravity can be produced by an accelerated frame of reference. An observer in a closed room cannot tell which of the following is true. Objects are falling to the floor because the room is resting on the surface of the Earth and the objects are being pulled down by gravity. Objects are falling to the floor because the room is aboard a rocket in space, which is accelerating at 9.81 meters per square second and is far from any source of gravity. The objects are being pulled towards the floor by the same inertial force that presses the driver of an accelerating car into the back of his seat. Conversely, any effect observed in an accelerated reference frame should also be observed in a gravitational field of corresponding strength. This principle allowed Einstein to predict several novel effects of gravity in 1907, as explained in the next section. An observer in an accelerated reference frame must introduce what physicists call fictitious forces to account for the acceleration experienced by himself and objects around him. One example, the force pressing the driver of an accelerating car into his or her seat, has already been mentioned. Another is the force you can feel pulling your arms up and out if you attempt to spin around like a top. Einstein's master insight was that the constant, familiar pull of the Earth's gravitational field is fundamentally the same as these fictitious forces. The apparent magnitude of the fictitious forces always appears to be proportional to the mass of any object on which they act. For instance, the driver's seat exerts just enough force to accelerate the driver at the same rate as the car. By analogy, Einstein proposed that an object in a gravitational field should feel a gravitational force proportional to its mass, as embodied in Newton's law of gravitation. Physical consequences. In 1907, Einstein was still 8 years away from completing the general theory of relativity. Nonetheless, he was able to make a number of novel, testable predictions that were based on his starting point for developing his new theory, the equivalence principle. The first new effect is the gravitational frequency shift of light. Consider two observers aboard an accelerating rocket ship. Aboard such a ship, there is a natural concept of up and down. The direction in which the ship accelerates is up, and unattached objects accelerate in the opposite direction, falling downward. Assume that one of the observers is higher up than the other. When the lower observer sends a light signal to the higher observer, the acceleration causes the light to be redshifted, as may be calculated from special relativity. The second observer will measure a lower frequency for the light than the first. Conversely, light sent from the higher observer to the lower is blue-shifted, that is, shifted towards higher frequencies. Einstein argued that such frequency shifts must also be observed in a gravitational field. This is illustrated in the figure at left, which shows a light wave that is gradually redshifted as it works its way upwards against the gravitational acceleration. This effect has been confirmed experimentally, as described below. This gravitational frequency shift corresponds to a gravitational time dilation. Since the higher observer measures the same light wave to have a lower frequency than the lower observer, time must be passing faster for the higher observer. Thus, time runs more slowly for observers who are lower in a gravitational field. It is important to stress that, for each observer, there are no observable changes of the flow of time for events or processes that are at rest in his or her reference frame. 5-minute eggs as timed by each observer's clock have the same consistency, as 1 year passes on each clock. Each observer ages by that amount. Each clock, in short, is in perfect agreement with all processes happening in its immediate vicinity. It is only when the clocks are compared between separate observers that one can notice that time runs more slowly for the lower observer than for the higher. This effect is minute, but it too has been confirmed experimentally in multiple experiments, as described below. In a similar way, Einstein predicted the gravitational deflection of light. In a gravitational field, light is deflected downward. Quantitatively, His results were off by a factor of 2. The correct derivation requires a more complete formulation of the theory of general relativity, not just the equivalence principle. Tidal effects. The equivalence between gravitational and inertial effects does not constitute a complete theory of gravity. When it comes to explaining gravity near our own location on the Earth's surface, noting that our reference frame is not in free fall, so that fictitious forces are to be expected, provides a suitable explanation. But a freely falling reference frame on one side of the Earth cannot explain why the people on the opposite side of the Earth experience a gravitational pull in the opposite direction. A more basic manifestation of the same effect involves two bodies that are falling side by side towards the Earth. In a reference frame that is in free fall alongside these bodies, they appear to hover weightlessly, but not exactly so. These bodies are not falling in precisely the same direction, but towards a single point in space, namely, the Earth's center of gravity. Consequently, there is a component of each body's motion towards the other. In a small environment such as a freely falling lift, this relative acceleration is minuscule, while for skydivers on opposite sides of the Earth, the effect is large. Such differences in force are also responsible for the tides in the Earth's oceans, so the term tidal effect is used for this phenomenon. The equivalence between inertia and gravity cannot explain tidal effects. It cannot explain variations in the gravitational field. For that, a theory is needed which describes the way that matter affects the inertial environment around it. From acceleration to geometry in exploring the equivalence of gravity and acceleration as well as the role of tidal forces, Einstein discovered several analogies with the geometry of surfaces. An example is the transition from an inertial reference frame to a rotating reference frame. This is analogous to the transition from a Cartesian coordinate system to a curved coordinate system. A deeper analogy relates tidal forces with a property of surfaces called curvature. For gravitational fields, the absence or presence of tidal forces determines whether or not the influence of gravity can be eliminated by choosing a freely falling reference frame. Similarly, the absence or presence of curvature determines whether or not a surface is equivalent to a plane. In the summer of 1912, inspired by these analogies, Einstein searched for a geometric formulation of gravity. The elementary objects of geometry, points, lines, triangles, are traditionally defined in three-dimensional space or on two-dimensional surfaces. In 1907, Hermann Minkowski, Einstein's former mathematics professor at the Swiss Federal Polytechnic, introduced a geometric formulation of Einstein's special theory of relativity where the geometry included not only space but also time. The basic entity of this new geometry is four-dimensional spacetime. The orbits of moving bodies are curves in spacetime. The orbits of bodies moving at constant speed without changing direction correspond to straight lines. For surfaces, the generalization from the geometry of a plane, a flat surface, to that of a general curved surface had been described in the early 19th century by Carl Friedrich Gauss. This description had in turn been generalized to higher dimensional spaces in a mathematical formalism introduced by Bernhard Riemann in the 1850s. With the help of Riemannian geometry, Einstein formulated a geometric description of gravity in which Minkowski's spacetime is replaced by distorted, curved spacetime, just as curved surfaces are a generalization of ordinary plane surfaces. Embedding diagrams are used to illustrate curved spacetime in educational contexts. After he had realized the validity of this geometric analogy, it took Einstein a further 3 years to find the missing cornerstone of his theory: the equations describing how matter influences spacetime's curvature. Having formulated what are now known as Einstein's equations, he presented his new theory of gravity at several sessions of the Prussian Academy of Sciences in late 1915, culminating in his final presentation on November 25, 1915.